Hello, my name's Jeremy Stacey. I'm an architect and I'm going to talk a bit about the principles behind the low energy work Nadia and Zachary have done at their house. To start with, I'm going to just draw a very simple house to use as a means of showing the principles. So here we have a very simple house which has brick walls and a timber roof, first floor. Now, one of the best ways to look at low energy work on existing buildings is to see what the existing building has to give you. And in the case of Nadia and Zachary, they have solid brick walls. Now, this is to their advantage because bricks have a high thermal mass, and that means that they absorb heat and then give off the heat very slowly. Whereas if they were a lightweight material, it might still absorb heat, but the heat will leave it very quickly. And so Nadia and Zachary wanted to exploit what they already had. And this is a very good way of working with existing buildings. So what we want to do is imagine the brick walls to be like large night storage heaters. So the brickwork will heat up from the heat within the rooms, developed from the heating systems, the cooking, the lighting, and from people. We want the brick walls to absorb that heat. So we need to insulate on the outside of the brick walls. So the brick walls will probably be one brick, or in some cases 1.5 brick thick, which is about 225 or 330 millimeters thick. And we put on the outside of the brick walls thermal insulation. And this is an idealised little house, but at Nadia and Zachary we could do this on the sides and the back of the house. So here we have these solid brick walls, insulated on the outside, and the insulation is protected by a modern silicon-based thin render. So this means that all the heat inside the house, the bricks absorb that heat. And because we've insulated on the outside, the heat doesn't dissipate to the atmosphere, but when the temperatures drop inside, the walls give back the energy that they've absorbed when the heating system was on. Not only do we need to address the walls, but we also need to address the roof. Now, ideally, we would place about 200 millimeters of insulation on top of the roof. But because Nadia and Zachary's house is joined to the adjoining building, that opportunity doesn't present to ourselves. So we need to insulate between the rafters. I mentioned that ideally we would put the 200 millimeters of insulation on top of the rafters, so the rafters will be kept warm. Just as we did with the walls, we're trying to keep the walls warm. But because we're in a conservation area and we can't do that, we need to think in a different way. What we're trying to do is avoid a thermal bridge. Now, a thermal bridge is where there is a direct route between outside and inside. Now, at rafter level, if we imagine here's a rafter, and above the rafters we have a breathable membrane, and then the tiles. We have our insulation between the rafters, which is all good. Because we couldn't raise the roof by 200 millimeters, what we need to do is put insulation underneath the rafters. And the insulation underneath the rafters needs to be slightly thinner than the insulation above. Otherwise, we get risk of a condensation occurring between the insulation layers. But now you can see that there's no direct route to the outside because we've insulated under the rafter. But as you can see, there's a difficulty at the edges. So if I draw a section through the wall, here's our brickwork wall, and here we come to the top of the wall, and here's the rafters, and we've insulated between the rafters and under the rafters. We need to take our insulation and the roof tiles over the top of the wall. Here's the original end of the roof. We need to extend that so that the tiling goes right across to the edge of the insulation, and this is filled with more insulation. So in the end, we have continuous insulation layer right across the building. So in effect, we're putting a warm overcoat right over the building, and we're avoiding thermal bridges. I'd like to talk a bit about the windows. Windows are an essential part of trying to achieve a low energy result. Ideally, they should be triple glazed and firmly broken. And I'll just draw a window. Just imagine this simple block is a window. Heat will just pass straight through the window. So we need firmly broken windows. And firmly broken windows are normally aluminium on the outside, timber on the inside, with an insulating material separating the outside from the inside. And this means that less heat is going to go from the inside of the building to the outside. Now, placing the window in the wall is also important. And if I draw a simple drawing of a wall, this is a plan view of the opening in the wall. Here's the outside windowsill. Here's the inside windowsill. And we've got the window in here, which Nadia and Zachary found when they moved in. Now, a number of things here, of course, because they were solid windows and not firmly broken, heat or cold just comes straight through the window. Also, you lose heat through the brick wall to the sides of the window on the outside. So we want to look at another way of putting the windows in the wall. Now, to reduce the thermal bridge between inside and outside, we need to position the insulated part on our modern windows over the joint between the inside and outside. And here's our aluminium facing of the window. And here's our timber internal component of the window. We take the render on the outside of the insulation into the reveal to protect the reveal. The windowsill now moves out to here on the outside. We've got the plaster on the inside, but there's still a slight risk of a thermal bridge through here. So we put an insulated lining on the inside of the window. So you don't see so much of the window frame on the inside. And here's our window in here, and here's the windowsill on the inside. And our window is triple glazed with 3 layers of glass. By moving the windows further out, we cover this gap in here, which can be a thermal bridge, because the modern high performance window has an element of insulating material within the build-up, separating the timber from the outside. These really show the ideal way in which we insulate an old building. Now, it's not always possible to do that, because we might, for example, be in a conservation area. So in a conservation area, we have to be generous to the needs of the historic building. And this means we can't always do what ideally we would want to do. Now, this is the case with Nadia and Zachary, and we had quite a bit of a battle with the planners in order to achieve this solution. And working with planning authorities, there always has to be a two-way process. And I find it's much better to find a way which you can compromise, which isn't to the detriment of the design intent, but goes along with the planners or conservation officers' requirements. So it has to be a two-way process. If you stick your neck out and demand something, you probably end up with going to appeal, and you may in the end lose the appeal. And at a certain level, this two-way process worked to our favour in the end, because in Nadia and Zachary's house, there were very lovely internal cornices running round the rooms. Now, on the outside of the building, there are also nice details. There's a projecting bay, which had a nice roof, and there were bay windows upstairs with nice roofs. So if we insulated on the outside, as we did on the side and rear elevation, we would lose some of the detail of the building. And so here we decided to put insulation on the inside up to windowsill level. And this is done with timber stud work, filling the gap between the studs with insulation, and just as we did at roof level, putting another layer of insulation over the studs. So if I draw at a larger scale, our timber studs, insulation between the studs, another layer of insulation over the studs, plasterboard, and then taking the windowsill right across to cover that. Now, we could keep the decorative cornices above. If we had taken the insulation right to the top, we'd have lost that. And because on the front elevation there's quite a large window area, we didn't really lose much heat because the wall area above was very small. The windows here couldn't easily be triple glazed because a triple glazed unit is much wider than a double glazed unit, which is probably about that wide. Triple glazed, probably that wide. The house is a really pretty house, and the windows at the front make a large contribution to the nature of the building. So we wanted to keep those. And so instead of triple glazed windows, we used a form of acoustic glass, a double glazed unit, where one layer was a great deal thicker than the other layer. So although it's slightly wider than a double glazed unit, it would fit into the format of the traditional window and the traditional casements on the front of the house. And the double glazed acoustic glass, because of the thickness of one of the layers, has a better insulation value than standard thermal double glazed units. And this approach has been adopted on all the front elevation. So up to windowsill level, and where the radiators in the house were placed, so we reduced our heat loss behind the radiator, and we had 175 millimetres of insulation there. And that worked well with the existing features of the house. The last area we need to look at is at the ground floor. Now, the ground floor in the house is a raised ground floor. It has a void underneath the floor joist. Now, if we were starting afresh, we would put in a new concrete floor with between 4 and 6 inches of insulation underneath the concrete floor. But it's not always possible to do that on existing buildings, and so we have to choose the next best option. And here we put a great deal of insulation between the floor joists and a bit of insulation underneath the floor joists. There is a risk of a thermal bridge between the floor joists, but we try and reduce that by taking our external insulation lower than floor level. So this is not ideal, but this helps us reduce the heat loss because the root of the heat from the inside of the building is covered with the outside insulation. I want to talk a bit about the way we heated the house. And we heated the house by electricity. Nadia and Zachary were very keen from inception of the project not to have a gas boiler. What we're looking for on the ground floor is use the whole floor as a large radiator with underfloor heating under the timber floor. And the way we wanted to produce the hot water to go through the pipelines underneath the floorboards was using a heat pump. Now, if I draw the principle of a heat pump, which is relatively simple, it uses a refrigerant gas. So in the pipeline, there's a refrigerant liquid. Now, a fan blows air over the liquid. The refrigerant liquid takes the heat from the air, and in the process, the liquid turns into a gas. And that goes round the system. And in this system, there's a compressor. As the gas is compressed, it gets even hotter. And so the hot gas then goes through a heat exchanger, which, if we look at it in very simple terms, it's the hot gas going through a tank of colder water. And because heat flows from hot to cold, the gas gives off its heat to the cold water. And in here, the cold water, there's another circuit which goes into the house. Now, that circuit is running at probably between 35 and 45 degrees centigrade. That goes into the floor, and under floorboards, you don't really want the temperature to go above 28 degrees. Otherwise, the wood starts to warp and crack, and you have problems in the floor. So heat pumps are ideal for heating underfloor. From the start, Nadia and Zachary were extremely keen to have as much of their roof as possible covered with photovoltaics. This caused a great deal of issues with the planning authority, and I think they were unreasonable about that. Zachary went round photographing many houses in the neighbourhood which had photovoltaic panels on the roof, and actually not really placed in a particularly architecturally relevant way. So what we did was place the panels recessed in the surface of the roof, and this allows the roof surface to be almost flush with the solar panels. And we have a large number of panels both at the front and the back of the house, and this goes a long way to generate electricity, which is stored in batteries, so you don't need to tap into the grid. You can use the battery supply when there's power in the battery. So on very warm sunny days, you're probably producing enough to run normal household appliances. Any storage any extra gets put into batteries, stored for when the sun is out. And this has been an eye-opener for me as an architect, and it just shows how the commitment of a client to reducing carbon emissions is a very powerful design intent to the whole project. Finally, I'd like to talk a bit about the overall approach to reducing global warming. Global warming is the greatest threat to humanity and the natural world, and we really do need to reduce carbon emissions from our home. We won't all be able to do it in the way we've achieved from this house, partly because of cost, or because of planning restrictions, or because the existing building is such that it doesn't allow us to do that. So in some houses, just putting 400 millimetres of cheap insulation in the loft is a really good start. Another good start is to avoid air leakage. So if the windows aren't fitted properly, so if we see cracks anywhere in the house, if you can see outside from the inside, you know that there's a heat loss. Now, with casement windows fitting into a frame, it's very important to have good seals. So when the window's shut, the window is tightly sealed in the frame. And often on old buildings, the casements don't fit tightly, or there may be no weather strip between the inside and outside. And so that's another very easy, low-cost way to reduce heat loss. Sometimes in old buildings, if you see air through the floorboards, it's time to think about the heat loss through the floor. At roof level too, even when you've got lots of insulation, you may find gaps at the top of the walls which allow a route of heat loss from the wall to the outside. So there are many simple ways one can reduce heat loss. But one step can be to wear warmer clothes in the winter and get used, if one's in good health, to having a lower internal temperatures. We're seen nowadays to all be used to working in offices in t-shirts in the winter, whereas in fact it's quite possible to work in an office with warm clothes and lower temperatures. So if you're in good health, turn the thermostat down, wear warm clothes, and also take regular exercise, because being in good health, both mental and physical health, helps us reduce our need for high internal temperatures. And finally, if all that's not possible, I say that to reduce the consumption of meat is another way of contributing to reduction in global warming. Thank you.